Will be Alex Cojocaru, and he will be talking about a computational test of quantum contextuality.
Thank you so much, Elise. Yeah, so in this presentation, I'll be talking about our work on a computational test of quantum contextuality and even simpler proofs of quantumness. And this is a joint work with my collaborators, Andrea, Coladangelo, Atul, Arora, and Kishor, Bharti. So our story begins in 1934 when Einstein, Podolsky, and Rosen argued that quantum mechanics is not a complete description of nature. And in particular, they show that following widely held physical assumptions, there exists a situation in which observables should have well-defined values, and yet quantum mechanics fails to specify these values precisely. 30 years later, and as a result, they conjectured that there should be a way to complete quantum mechanics in that sense. So 40 years later, Bell, Clauser, Horn, Shimoni, and Holt introduced the notion of non-local games. And in this way, they settled this philosophical question by proposing an experiment that involved spatially separated systems, as illustrated here. And in particular, they show that in this setting, there exist some correlations between the inputs x, y, and the outputs a, b that quantum mechanics can produce, and yet no local hidden variable model, or in other words, no complete theory in the sense envisioned by EPR, can produce such correlations. So a few years later, Bell, Cohen, and Specker introduced the notion of contextuality as a way of ruling out an even larger set of complete theories. And in particular, the main question they addressed is whether spatial separation is really needed to rule out such complete theories. And for this, they give a partial answer, proving that, in fact, the spatial separation is not really needed. So in particular, their starting observation was that in non-local game, as observables are acting on spatially separated subsystems, these observables also commute. And as a result, the question they addressed is what happens if we try to relax the spatial separation and instead only consider commuting observables, but which this time act on a single system. And they show that indeed, if one considers this setting in which we are acting with commuting observables applied this time in a sequential way, but on a single device, there exist some correlations between the questions Q1, Q2, and the answers A1, A2 that, again, quantum mechanics can produce, and yet no complete theory is able to produce such correlations. But unfortunately, contextuality games suffer from an inherent limitation because, as opposed to the non-local game setting, for contextuality, there is no satisfactory experiment. And this is exactly the main issue that our work is addressing. Particularly, our main result focuses on constructing such an experiment or operational test of contextuality under computational assumptions. So to describe our compiler, we first recall a recent breakthrough result due to Carlyle, Lombardi, Vaikuntana, and Tan and Yang that show that essentially the spatial separation in any non-local game can be enforced within subsystems of a single quantum system using cryptography. On the other hand, in our work, we show that if one considers a contextuality game, then we can enforce the temporal separation in any contextuality game by restricting the communication between sequential measurements of a single quantum system, again using cryptographic tools. So the key idea in QIP is very elegant. In particular, they consider a non-local game as the one illustrated here, and then compile it into a two-round protocol in which in the first round, we are going to encrypt the question corresponding to Alice and receive a corresponding encrypted answer. And for the second round, we are going to simply ask the question corresponding to Bob in clear and receive the corresponding answer. And at a high level, what they show is that there exists a quantum device for this compiled protocol that can produce stronger correlations between the encrypted messages corresponding to Alice in the first round and the clear messages corresponding to Bob in the second round. And these correlations are stronger than any correlations produced by any classical efficient device. Unfortunately, if we try to directly apply this idea for contextuality games, we run into this major issue, because in contextuality, we have a single system. And as a result, if we are going to apply the first question under encryption, then this also in particular means that the post-measurement state is going to be an encrypted state, and hence, there is no obvious way how to ask the second question in clear. So we are going to show how to circumvent this issue by introducing a novel re-encryption procedure followed by an effective decryption step. So in particular, at a high level, our result can be understood as follows. Since any non-local game is a contextuality game, but not the other way around, then our compiler is able to compile a strictly larger set of games. Additionally, we also formalize this notion of operational test of contextuality as a strengthening of the notion of proof of quantumness or quantum advantage, and we show that our compiler satisfies this stronger notion of operational test of contextuality. So now, equipped with this, we are able to formally define a contextuality game. So in analogy with a non-local game, a contextuality is also going to be specified by a tuple that can be expressed as follows. So we have A representing the set of answers, Q represents the set of questions, and C all represents the set of all contexts. Where for a context, you can simply think of it as just being a subset of the questions that essentially can be asked at the same time. And now this is going to be a probability distribution that is going to be used when we are going to sample a context. And pred denotes a predicate that will allow us to evaluate a player's strategy against the contextuality game. So finally, the value of a contextuality game is going to be given by the following expression, in which roughly we are first going to sample a context according to the distribution, and then we are going to consider a player strategy. A player strategy is given by its set of answers from A1 up to AK for a given context C. And finally, we simply evaluate that player strategy using the predicate pred. So now, when one considers contextuality games, there are two main families of strategies that one can use. So the first family refers to non-contextual strategies. These are the analog of local hidden variable strategies, and you can intuitively think about them as just being convex combination of deterministic strategies, where a deterministic strategy is simply going to be given by a truth table, by a function from the set of questions to the set of answers, that is going to assign a deterministic fashion for each question Q a corresponding answer AQ. And hence, when one considers such a strategy, so when given a context C given by a set of questions Q1 up to QK, then such a player is going to respond with the corresponding answers given by this truth table. And the second main family refers to contextual quantum strategies. These, on the other hand, are given by a quantum state psi and a collection of observables parameterized by the set of questions such that these observables are going to commute in a context. So two important observations I want to make here. So on one hand, if we speak about the first family of strategies, the non-contextual ones, then if a question is going to appear in multiple contexts, then such a strategy, the answer in such a strategy is going to be independent of the context in which the question appears. And the second main observation is that for any key-player non-local game, you can think of it as just being a contextuality game with context of size k. Okay, so now let us revisit in a bit more details the main idea behind the KLVY compiler. So essentially, they are able to convert any non-local game G into an interactive protocol, where the high-level idea is that the spatial separation in any non-local game G can be replaced by the use of cryptographic assumptions. In their case, by the use of a quantum fully homomorphic encryption scheme. So a bit more concretely, if one considers a non-local game as the one showed here, then their compiler transforms it into a protocol between a classical verifier and a quantum prover that can be summarized as follows. So the verifier is going to first sample the questions corresponding to Alice's and Bob's question, and is going to encrypt Alice's question and send the encrypted question to the prover. And then the prover is going to simply measure the first subsystem corresponding to Alice's subsystem using this encrypted question, so under quantum fully homomorphic evaluation, and is going to obtain a corresponding answer that is going to be sent back to the verifier. So the verifier can then simply decrypt this answer, and then he will move on to the second question. But this time, the verifier will simply send the question corresponding to Bob in clear. And the prover will proceed by measuring the second subsystem using this question and obtain a clear answer that will be sent back to the verifier. And finally, the verifier, all it has to do is just to evaluate the predicate of the non-local game G on the questions and the answers obtained from the prover. And if predicate evaluates to 1, then we say that the prover has won this game. And the main result of KLVY says that for any non-local game G, the compiled game is going to satisfy the following two conditions, assuming the correctness and security of the underlying encryption scheme. So the completeness says that there exists a quantum polynomial time prover that can make the verifier accept in this compiled protocol with probability at least the quantum value of the non-local game G. And the security or the soundness says that any classical polynomial time prover can only make the verifier accept with probability at most the classical value of the non-local game G. So now let's try to extend this idea of KLVY to contextuality games. So one direct extension could be the following protocol. So now the verifier in the first round would sample a context C, and then would pick a question from this context at random. After this, as before, it's going to send its encryption to the prover, and then the prover is supposed to measure the state of the system given this encrypted question. So similarly, you can intuitively think about it as doing this operation under homomorphic encryption. And then the prover is supposed to send back the encrypted answer, and finally, the verifier would proceed to the second round. So for the second round, the verifier is going to again pick another question from the context at random, and is going to send it this time directly in plain to the prover. And it's expecting an answer from the prover, and we then have like a final evaluation. So the verifier first checks that if the two questions are equal, then it's going to accept the prover if and only if the two answers are equal. And if the questions are different, then it's going to accept if and only if the predicate of the contextuality game is going to evaluate 1. But of course, we are going to run into this issue that we have just explained before, namely that if the first question is going to be asked under QFHE, then this also means that the post-measured quantum state is also going to be encrypted. And in particular, this implies that even an honest quantum prover is going to be unable to execute a quantum strategy for the contextuality game. So now we are able to give our final construction that in particular solves this main challenge. And here I'm just going to emphasize on the main differences from the previous construction. And the first observation I want to make is the form of the encryption being used. So again, for those of you that are familiar with quantum fully homomorphic encryption, you might notice that this looks like a generalization of that, in which we are now considering a family of unitaries. So in particular, this encryption consists of a quantum part, where the quantum part just applies a unitary from a family of unitaries indexed by a key k. And the classical part of this encryption is just a classical encryption of this key k. So now for the first question, on top of just sending the encrypted question, the verifier is also going to send the public key for a re-encryption procedure that I'm going to describe soon. And now, after performing this measurement under encryption, we also know, due to this encryption form, that the post-measurement state is also going to have a similar form, so it's going to have a classical encryption part. And now here is where the re-encryption step occurs. So you can intuitively think about this re-encryption as the prover just adding a second layer of encryption on top of the encrypted post-measurement state. So a bit more formally, if we think that psi-Q1A1 would be the plain post-measurement state after performing the observable Q1 and obtaining the answer A1, then because this measurement was done under encryption, we have a first layer of encryption given by UK. And then because the prover added the second layer of encryption, then we also are going to have this second UK prime. And now the verifier can, knowing S and S prime, can decrypt both S and S prime, and can essentially compute key effective, where you can simply think about this key effective as just the key obtained by combining the two layers of encryption. So more precisely, as mentioned before, if we think that we had the first encryption coming from performing the post-measurement, after performing the measurement under encryption, and the second layer of encryption after this re-encryption step, then combining the two layers of encryption gives us a new encryption, but under a new key effective. And for the second question, the verifier is going to simply send this key in plain to the prover. So what this allows a quantum prover, so on one hand, it allows such a quantum prover to essentially remove the two layers of encryption all at once. And in this way, he has again the clear post-measurement state on which he can now apply the second question in clear and obtain the corresponding answer. So in particular, this re-encryption procedure must satisfy the following property, that for a classical polynomial time prover, such an attacker cannot distinguish between the final combined key effective, and the uniformly random string. And in particular, this implies two things. So on one hand, if we speak about a classical polynomial time prover, then this means that such an adversary is not going to gain anything from verifier's response. So in particular, it's not going to learn anything about, it's not going to learn anything from key effective about the first question. Because it was, recall that it was essentially that the first question was under encryption, and the security notion says that such an adversary cannot learn anything about Q1. And hence, it must act as having no memory, and thus will follow a non-contextual strategy. And the second point, it says that for a quantum polynomial time prover, such a prover is going to be able to recover the post-measurement state, as mentioned by removing the two layers of encryption all at once, and hence it will be able to apply a quantum strategy and behave contextually. So now I just want to define a bit more formally this re-encryption procedure. So you can essentially think of it as just consisting of a tuple of three algorithms, a generation, encryption, and a decryption. And yeah, we call this re-encryption procedure as an oblivious pad. And the correctness is that the form of the encryption is the one you have seen previously. And the security says that for a classical polynomial time prover, such an adversary cannot win the following security game with probability more than a half, where the security game is between a challenger and the classical prover, and the challenger is going to simply generate a public key and a secret key, is going to send a public key to the prover, and then the prover is going to reply with an encryption as prime. And then challenger is going to compute two keys, one which is uniformly sampled at random from the space of all keys, and the second key which just represents the encryption of S prime. And then it's going to send uniformly at random one of the two keys to the prover. And finally, the prover wins this game if he guesses correctly which key he received. And another property from this oblivious pad is required for our compiler to ensure that the compiler is faithful to the contextuality game G, where at a high level, this property says that there is a one-to-one map between the original contextuality game and the compiled one. But the main result says that this oblivious pad primitive can be constructed assuming the hardness of the learning with errors problem in the random oracle model. So now let us state our main result regarding our contextuality compiler. So on one hand, if we first consider contextuality games of size 2 consisting of two questions, then our compiler is going to first ask one of the questions under encryption and leave the second question in clear. And in this case, we get the following completeness and soundness guarantees. So the completeness says that there exists a quantum polynomial time prover that can win the compiled game with probability at least half plus the quantum value of the contextuality game divided by 2. And the soundness says that for any classical polynomial time adversary, they can win the compiled game with probability at most half plus the non-contextual value of the game G divided by 2. And our compiler can also be used for contextuality games of arbitrary size. And in that case, our compiler is going to encrypt the first C-1 questions and leave the last one in clear. And we will get similar completeness and soundness guarantees, but where the probabilities, of course, scale with the size of the context. So two important observations I want to make here. So on one hand, our compiler works for any contextuality games of arbitrary size, and is going to use only 2 rounds of interaction in total, which is independent of the context size. And in comparison, the KLVY compiler for non-local games is going to require 2K rounds of communication for K-player non-local games. But I should also add here that while our construction is in the random oracle, their construction is in the plain model. So that's also like an important difference. And the second remark is, as we mentioned before, that each compiled game is going to remain faithful to the original contextuality game, which very roughly says that there is a one-to-one map between the strategies in the original contextuality game and the strategies in the compiled game. So finally, I just want to conclude with some future directions. So the main open problem is regarding the quantum soundness. Because as opposed to the non-local game setting, particularly the KLVY compiler that we just described, some follow-up works, including one that have been presented at this conference earlier this week, have also showed an upper bound on the winning probability for quantum provers. And in particular, they show that these lower bounds match that of the underlying non-local game. And unfortunately, our contextuality compiler does not satisfy this property, as we only have classical soundness. So of course, this would be the main goal. And the second main open question is regarding this generic re-encryption procedure, the oblivious pad. Our construction is in the random oracle model, and of course, ideally, we would like to have a construction in the plain model that would also give us a compiler, a full compiler in the plain model. And secondly, ideally, maybe also once we have quantum soundness, one can find some other applications for these generic re-encryption procedures. And with this, I would like to conclude. Thank you.
Thank you. We have time for a few questions.
So I might be completely misunderstanding something, but I remember at the beginning you mentioned the contextuality game requires the commutativity relation between your two sets of measurements.
Between the observables acting on a single system, yeah.
Then when you do this encryption and decryption, how do you ensure these commutativity relations is still satisfied?
So basically, this is just taking a contextuality game that already satisfies these notions, and we basically are able to compile it into a protocol that has these completeness and soundness guarantees. So in particular, the input of the compiler already has these properties, and what we want to achieve is essentially that there is this gap between quantum polynomial time provers and classical polynomial time provers. I'm not sure if that answers your question.
I guess my question was like, I just have a little bit of confusion on whether your decryption part of the, like you have this decryption protocol that will affect the commutativity relation at all, or it's already building somehow and you can.
Yeah, so basically we are not actually changing the observables. It's basically the way they are interpreted in the compiled protocol. So we still have the first question that is going to be sampled from the context. And as you see, the main thing we are doing here is that the first question is going to be asked under encryption. So the prover can perform this encrypted measurement under some quantum homomorphic encryption scheme. And then we are going to decrypt the answer that is going to be used in the final evaluation. And then we proceed to the second round, in which we are again sampling another question from the context. And in between, we just need to introduce this re-encryption procedure to make sure that the prover is able to ask the second question as well.
Over there.
Hi. Yeah, sorry if this is like a really naive question. How does the polytime verifier calculate K effective?
So basically, so it kind of like depends on the form of the encryption being used. But if you think about like a quantum fully homomorphic encryption scheme, in that case, this U is simply just a quantum one-time pad. So basically, once you are able to compute K and K prime, then you can also compute the combining two quantum one-time pads and what are the corresponding keys.
I see, so
for this. Yeah, but very crucially, the verifier must first decrypt S and S prime to compute K and K prime. Okay. And once K and K prime are computed, then K effective is also easy to compute. But this can also be generalized beyond quantum one-time pad, but yeah, just to give an example here.
Thank you.
Okay, let's thank our speaker again.